Now the audio is there. You know, I can tell. I think I made the echo go away. Well, at least I made the echo go away for us. Totally incompetent. Should send him home. All right, so doctors kill people by making mistakes. I'm not going to go through the whole thing again. Ask one of your. You were talking about doctors, the fact that doctors kill people. Sometimes they make mistakes. It's one of the leading causes of death in this country is mistake by physician. What's the frequency of doctors killing people? Is it like 57 people per mistake? Yeah.
Wasn't there that one instance where a doctor killed 3 people by making a mistake?
I suppose it could be more than one, right? But what's the typical mistake to death ratio? It's probably much less than 1, right? Doctors probably make a lot of mistakes that don't kill you. But if we just look at the fatal mistakes, the typical ratio of mistake to death is 1. See if the slide works now. I have followed your advice. Maybe. No, I haven't followed your advice directly. Let's try again. How do engineers kill people? I got nothing.
In 1968, at the
All right, so how do engineers kill people? Same tool, right? Mistakes. Yeah.
Assume people know how to use the tool.
All right, so yeah, so they could make assumptions that people know things. What's the answer I'm looking for? I couldn't hear you. So weapons production, yeah, I did that on purpose to make you think of that. But so doctors typically can make mistakes, and they can kill people 1 person per mistake, right? When an engineer makes a mistake, it's not usually likely to hurt 1 person or kill 1 person, right? Engineers make mistakes that have much broader impact. And engineers can kill people by the thousands. Yeah, I mean, there's all kinds of examples that immediately come to mind. The one that jumps to my mind, because it was a WPI graduate involved, is the Tacoma Narrows Bridge. Now, this is a long time ago. Anybody know about the Tacoma Narrows Bridge? A bunch of hands go up. And so, did you know that the designer of that bridge was a WPI alum? Yeah, there's a picture of it. Well, I have no idea what's in Caven because you can't get in there right now. But there used to be a picture of the bridge, one of the hallways in Caven. So for anybody that doesn't know this story, they built this suspension bridge. You guys have all seen suspension bridges. It's like the Brooklyn Bridge is a suspension bridge. It's got the cables that hang down, hold the bridge up. Built a suspension bridge across a narrow part of strait near Seattle, Washington, and Tacoma, Washington. And the wind blowing up the valley would vibrate the cables. And it was positioned and spaced just perfectly so that those vibrations from the wind caused a harmonic resonance in the cables and then the bridge. And the bridge was doing this. And my grandparents lived in Seattle at the time when the bridge was in existence. They said that people used to go drive across it to feel the motion right up until the day where it got so bad the bridge fell down. There was one fatality when the bridge fell down. It was the designer's dog. The designer was out there. He was trying to figure out what was wrong. He was out there as the bridge and the waves started getting bigger and bigger, and he ran off the bridge. Bridge fell down. His dog didn't get off with him. But we all know of engineering mistakes that have killed people, and some of them have been significant. There was an engineering failure. We don't need to go into list a whole bunch of different engineering failures that have killed people. And so this video, and there's a link to it here in the slides, and you can watch the rest of the video. It's about an hour long. Oh, 28 minutes long. There's a longer version. This video talks about the founding of OSHA. And I want to watch just a couple more seconds here if I can get the echoing to not happen.
The height of the war in Vietnam, 14,000 Americans were killed and 46,000 were wounded.
All right, did anybody catch those numbers? Did anybody catch the numbers? Yeah.
14,000 killed, 46,000 injured.
14,000. All right, remember those numbers. I guess we got to see the. I'm never going to learn how to do this. So 14,000 killed, 46,000 wounded.
In 1968, at the height of the war in Vietnam, 14,000 Americans were killed and 46,000 were wounded. That same year, another 14,000 Americans were killed. But those lives were lost right here in the United States because those American men and women were killed at work, on the job. Another 2.5 million American workers suffered disabling injuries. That's 54 times the number of people we had wounded in Vietnam that year.
All right, the subcommittee will be in order. This morning, we're continuing.
2.5 million. So 68 is often called the bloodiest year of the Vietnam War. 46,000 wounded, 2.5 million wounded. Disabling injuries, they said. And so as a response to this statistic becoming apparent, Congress had hearings and they did stuff. They did Congress stuff, right? And they created OSHA. Anybody know what OSHA stands for? Anybody who's had a job? Who's had a job where there was OSHA? Somebody told you these regulations are because of OSHA, or the OSHA inspector is on site, anything like that. So do you know what OSHA is?
I don't know the name of it, but it's like regulatory rules to like create a set of like standards.
So they do develop regulatory rules and standards, and they enforce them. Yeah.
Occupational safety and health advisory.
Occupational safety and health, is it administration? Advisory? I think it's administration. But the key words here are occupational health and safety. And so OSHA came into existence to keep all of us safe when we're at our workplace. Did anybody ever worked at a company where the OSHA when an OSHA inspection happened? I have. Actually, here at WPI, there's been OSHA surprise OSHA inspections. I've seen that. I got an email once that said there was a surprise OSHA inspection yesterday, and as the person responsible for the safety of the facility, you get that instant of, "Oops, my heart didn't beat that time," right? Right, when you get the email, you read the subject line, "Surprise OSHA inspection yesterday." It was in a different lab on campus. It wasn't my lab. There was $17,000 in fines written from that surprise OSHA inspection. So one other company I worked at, the day I started, although I started a little bit later in the day, earlier that morning, they got a $10,000 fine from OSHA before the inspector got out of his car. It was justified, totally justified. It was a construction company. He pulled into the parking lot. He looks out the window of his car, and he sees somebody riding up out of a hole in the bucket of a backhoe. Fine, totally justified. Now, why did the guy ride up out of the hole in the bucket of the backhoe? It was certainly easy. In fact, I'm not certain he could have climbed out of that hole. He never should have been in that hole. That was the bigger problem. Because there's confined space rules, especially when you're dealing with holes in dirt. The risk there is the walls collapse, and then it's no longer a hole, it's a grave at that point, right? And so frequently that I worked for that company for several months. It was a summer job when I was in college. Even after that, the attitude didn't change on the work site. Even after that, it was us against them. We felt, as the employees, we felt that we needed to do something to make sure the company made money without having to obey these stupid OSHA rules. And so I remember one time later in the summer getting a call on the radio and saying the OSHA inspectors on site knock the handrails off the man basket. And so we had because of a big construction company, we're building roadway bridges, and we had a crane, and you use the crane to move materials around the workplace, and you take them off the back. You've got all seen it over here, right? Pick up the materials, maybe you put it on top of the bridge, or you put it down where it needed to be. Well, sometimes you needed to work like on the outside edge of the bridge. The easiest way to get that to that spot was to rig up a little basket, hang it from the hook on the crane, stand in the basket and have the crane swing you over there, and you could do your work that you needed to do. And of course, we had safety harnesses on. We were tied off to the basket. But if you had a man basket, this is a thing, is hanging from one of these baskets. If you have a man basket, it has to be inspected by a professional engineer every 6 months. There has to be a report for the inspection. And we didn't have a PE on site. We had a carpenter that knew how to make handrails, right? And so as soon as we knocked the handrails off, now it's just an equipment basket. Now we use that, we load up our jackhammers on top of it, and they put it up on the bridge. No longer against the rules. Even at the end of that summer, we're still circumventing OSHA so that the company could make more profit. Because why? I was doing it because I was a stupid 18-year-old kid, right? And that's what the guys were doing. That's what they told me to do. But why? Why were these career construction workers, people that commute 2 hours to work every day, why were these guys circumventing OSHA? Yeah.
The more the company makes, the more you make.
No. Not in that case, I'm pretty sure. They had a flat salary, and they got overtime if they worked extra. But in that case where you've got and it was a small business. I don't know, $2 to $5 million a year in revenue. Certainly, the more the company makes, the more the owner of the company makes in that situation there. But there was no profit sharing with the staff. In fact, they were all seasonal workers. They'd all get laid off for the winter. And then they get rehired in the spring because it was northern Vermont. And northern Vermont, you don't do a lot of construction in the winter, especially if you're building bridges. So it wasn't because the more the company makes, the more they make. But it totally was for the benefit of the company. They were afraid that if they didn't do these things, they would lose their job. 100% certain. They never even thought about it. It was automatic, that subconscious fear that if they didn't do these things, they would lose their job. Now, what's the purpose of OSHA? Yep. To keep them safe. Why do they need to stay safe? Yeah.
Most people prefer not to die.
Well, yeah, of course, most people prefer not to die. It's not just the chance of fatal incident, though. It's also if you, I mean, there's OSHA rules about repetitive stress injuries, right? So who's heard of carpal tunnel syndrome? Yeah. I have finally deduced, I haven't been to the doctor yet. Remember a couple weeks ago, I spent the day in the hospital? I'm pretty sure it's because of carpal tunnel syndrome now. I've done a bunch of research because I can't go to the doctor, so I do the WebMD, right? And so this whole arm, most of the time has like pins and needles, tingly, all the time. Sometimes is excruciating pain. And the theory was that it was in my neck and my shoulder. But the more and more research I do, turns out that nerve that runs from the back of your skull here down, it comes down around here, goes out to all your fingers, and it spreads out. So that nerve bundle, I don't know what they call it, it runs right through that wrist, right through the part that gets damaged with. I spent a lot of time running a jackhammer that summer, so vibrating machine tools, and then I've spent a lot of time operating a mouse, and I've spent a lot of time typing on a keyboard, and anyway, I read that the nerve could be pinched down here, and that could cause all that pain. And I started doing physical therapy exercises from YouTube to strengthen that wrist and to alleviate symptoms of carpal tunnel. And the pain pretty much went away in a week. I still have all tingly. Like right now, I can't feel the tip of my thumb. But is it because of infrequent rest periods while operating a jackhammer 30 years ago? Nobody, we'll never know that. But and I knew we were supposed to have a rest period every so many minutes, but the foreman didn't offer that. If I wanted to keep my job, I had to do what the foreman said, right? And so it's possible that I spent the day in the hospital 2 weeks ago because of that summer job. So even if you're just doing a part-time job, don't think it's okay to go around these safety rules. They weren't developed on accident. Okay, so OSHA is there to protect us. That's not the primary focus of today's lecture. So you guys raise your hand if you're an engineer. Right? You're all engineers now. You maybe don't have a degree yet, but you're all already engineers. And who thinks that maybe someday they want to be a professional engineer? So you want to take the PE exam, become a professional engineer, have a license. If you have a PE stamp, then they can sue you if you make a mistake. Just saying. I don't think that's a bad thing. Does anybody know what the first canon of ethics is for professional engineers? You'll have to know this when you take the PE exam. Pretty sure. Anybody? Yeah.
Is it the same one in vinyl letters, like right in front of
It is the same one that's in vinyl letters that you see every time you walk out of Washburn. Does anybody know what it says?
the safety and well-being of the general public?
Yeah, I think it says hold paramount, but whatever. So hold paramount the safety of the public. hold paramount the safety of the public. That kind of excludes making napalm bombs, doesn't it? All right, so hold paramount the safety of our public. The other guy's public, that's on them. My dad's a civil engineer. I always give him a hard time. As a mechanical engineer, I say, you guys build targets, we build bombs. Thank you for keeping us in business. Except he was a combat engineer, so one of his jobs was to blow stuff up. Anyways, let me get this off the screen. Next slide, right? So one of the ways we do this, we develop safety systems. And I want to think about, you guys have all been operating CNC machine tools throughout the term. So let's picture the Haas mini mill that we've been running throughout the term. Now, would you believe that there was people at Haas when they developed this, when they designed it and built it, that their foremost concern was the safety system associated with that machine tool? You'd be willing to believe that? And partly it's because they've got a lot to lose if you get hurt on that machine tool, right? Because in today's society, when somebody gets hurt, you sue everybody. So one reason is they have this interest in not getting sued, not having liability for you getting hurt. There's one reason that they have this safety system built into the machine. That's not the only reason though, right? They just don't want you to get hurt. They're not evil people, right? So they actually truly care about whether or not you get hurt. So what did the safety system on that mini mill, what are the components of that safety system that you can think of? And chalk, where'd I put it? Can't lose this little piece of chalk. Go ahead. So there's an emergency stop. What's another component of that safety system? Interlock switch. What else? What else is part of the safety system of the Haas mini mill? Yeah.
Like the entire enclosure.
The enclosure. What else? Yeah.
If you crash the machine, does it stop?
Overload. Yeah, so if the servo motors exceed a certain threshold, any of the servo motors, it shuts everything down. It puts it in the emergency stop situation. Yeah. So audio and visual indicators. Feels weird to say AV. It's not the club. But audio visual indicators. So the newer ones have a flashing light on top. Flashing green means I'm done with my program. Solid green means I'm running a program. And flashing red means something's wrong. The coolant. So the purpose of the coolant is, one, to reduce the friction in the cutting area, and two, to pull heat out of the cut. Is the coolant? I never had that question before. I'm going to put it on the side. I think it's really more for the efficiency of the cutting operation, but you certainly could build up too much heat and cause something to break. So maybe. What else? There's a big one we missed. Two that I can think of. One did not come from Haas. So maybe that one doesn't count. Yeah. So we have our safety checklist. We missed a pretty substantial one that does come from Haas. Anybody notice all the stickers that tell you do this, don't do that? Warnings. There's also a manual. So we've got the manual, the emergency stop. I might even include the light. Right? If you cannot, the light allows you to see what's going on inside as the operator. Excuse me. So the light, I might even include as part of the safety system. Now, it's not the only function of the light, right? It also just simply lets you operate. But, all right, so the manual. How's the manual part of the safety system? I put it there. You guys didn't. But how's the manual part of the safety system? Sure, there's a whole section in the manual about safety and about things that you should not do. But it also empowers you to know how the machine works. If you know how the machine works, it's more likely that you can use it safely. So part of safety is training. So it would be unsafe to set you free with no guidance until you go use those machines and make some parts, right? So as we move to a higher level and we start thinking about the safety system for the room that the machine is located in, we need to have training and we need to have some way to measure the training of the operators. Does that make sense? All right, so the manual is for training. Now, what's the function of the e-stop? That's the first thing we put on our list, right? It stops the machine. Does anybody know how it stops the machine or the manner in which the machine is stopped when you use the e-stop? Yeah.
It just cuts the power to everything that moves and could be dangerous with power.
So many e-stops just cut the power. The e-stops on these CNC machines don't actually cut power. They supply power. So when you hit the emergency stop, it actually supplies power so that it can do braking of the servo motor. So it stops the spindle. It stops the motion of all the axes. They still have power, but it stops them and holds them in place at that moment. Now, there's room e-stops, right? You see them on the columns as you walk through the room. If you press that room e-stop, it shuts down the power to all the circuits that plug in all the machines. What's the difference now if you press the e-stop on the machine tool as opposed to pressing the e-stop on the wall?
Probably quicker because the first one on the wall, the spindle has to slow down.
Right, so the spindle has momentum. So if the spindle's operating, if the incident you're trying to react to involves the rotation of the spindle, which usually it does, then pressing the one on the wall doesn't do anything to actively stop the spindle. It simply cuts the power to it. Whereas if you press the one on the side of the machine tool, it actively stops. It actually applies. Have you seen on the back of the machines? You may not have noticed this. Anybody notice there's like stove burners on the back of the machines? It's a giant resistor. It's where the heat goes when the servo breaks. All it is a giant resistor. I've heard rumors of people warming up their coffee on there. You could write a program to start and stop the spindle really quickly, and then that would heat up the element. You could make coffee. I haven't seen it myself, that I will admit to. All right, so the emergency stop stops that. So how does that make us more safe? Yeah.
I'd much rather have the spindle stop immediately than have to wait for it to stop turning.
Yeah, with either version of the emergency stop, how does stopping the spindle make us more safe? Yeah.
It prevents if thing goes catastrophically wrong, you don't have pieces of metal flying everywhere.
Right. So if there's a catastrophic failure, what makes pieces of metal fly everywhere? The energy that comes from that rotation, right? If it's the tool that comes apart. There's a bunch of energy in that tool when it comes apart. If you stop containing the location of the tool because the tool is broken, it flies in all different directions. So if we can anticipate that the tool's about to come apart and we hit the e-stop, there's less chance that the tool's going to fly in all directions. Now, what does the door interlock do for us? Yes. Right, it keeps us from being stupid, or it keeps the stupid version of us from interacting with the rotating part of the machine tool or the pinching part of the machine tool, right? You could get yourself squished between the table and the back of the machine, or between the table and the front of the machine. So it keeps us out of the machine tool. And they can work in different ways. And actually, there's settings on the machine. Some of them will put the machine in alarm state. So as if you had pressed the emergency stop just by opening the door. Some of them will simply slow down the rotation of the spindle. And so that's, and there's standards for this, and there's different standards apply in different countries. And so I'm not sure which one does which. Don't make assumptions about what it's going to do in a particular machine, especially when you go somewhere else, without finding out. Easy way to find out would be to start the spindle and then open the door just a little bit and see what happens. As long as it's not a dangerous situation. And sometimes the newer machines, you can't even open the door. As soon as the spindle starts, a lock engages and you can't physically open the door until you stop the spindle. Kind of like your front-loading washing machine. Front-loading washing machine has a door interlock also. Maybe even the top-loading ones. I think it does. It's enacted at different times. All right, so the enclosure, what's the enclosure do? It's kind of obvious, right? Yeah. It keeps the chips, it keeps the tool, it keeps all the stuff from hitting us. Did I share with you the video of when this didn't work out? No. I don't have a link to it in this presentation, but I will send you a link to a video that shows what happens when the enclosure is insufficient. I'll paraphrase for anybody who doesn't want to watch the video. That a tool, so the tools actually have a maximum speed rating on them. So different tools, depending on how they're balanced, how heavy they are and things, there's a maximum speed at which you're allowed to spin them or supposed to spin them. The operator in this case accidentally spun a tool that was supposed to spin at maybe 5,000 RPM at 12,000 RPM. So double the speed that it was supposed to spin at. And it put some undue stresses. You've seen how the tools get held in the machine tool. There's the little nut at the, or bolt at the top. We call that the pull stud. There's a little clamp that grabs that and spring-loaded pulls it up into the friction of the mating tapers. So the pull stud broke because of excessive vibration because the tool was not balanced. Pull stud broke. What happens when the pull stud breaks? Tool falls out of the spindle, right? Gravity. Gravity happens. And of course, gravity happens fast because it was a heavy tool. Too heavy. So pull stud breaks. Maybe that wasn't the first thing that broke. I think they thought the counterweight came off. So there's a big arm sticks out like this, the balancing counterweight on the other side. It was first the counterweight came off. Then the pull stud broke and it fell out of the spindle. So the tool that fell out of the spindle, it hit the vise that was bolted to the table. It broke the vise in half.
Would it have done that if you would have just dropped it without the...
No, it had to be the energy from the spinny spin. Broke the vise in half. And knocked it off the table. So this was all debris down at the bottom of the machine tool. I mentioned the counterweight came off first. That was what caused the unbalanced spinny spin, which caused the pull stud to break. When the counterweight came off at 12,000 RPM and weighed, I don't know, 5-10 pounds, it went out the back of the machine. It went through the wall. It went through the chair that somebody normally sits in. Person wasn't there. Threw the chair 30 feet across the room, glanced off like a block wall, concrete blocks, breaking the block that it hit, but didn't penetrate it. It was a sort of a glancing blow. Went through another wall and ended up in the office area. Because the operator accidentally spun the tool too fast. Nobody got hurt, near miss. But sometimes the enclosure is not enough. And there was an airplane incident recently, right? Not too long ago, where the engine blew up and the parts of the engine made a hole in the side of the airplane. It's on YouTube. You can find it. It was an A320, I think. So I once sat next to the guy who worked at one of the jet engine manufacturers on an aircraft, and we're flying back. And he said, my job is to design the safety shrouding that makes sure all the engine pieces stay inside the engine when it catastrophically fails, right? So that's a safety system, right? So you want to design it so that it doesn't fail. But in the event, you hit a frozen turkey or a flying turkey, doesn't matter. Sometimes the turbine blades come off, right? So he said, don't sit next to the engine on the airplane. The guy that designs the safety shrouding, he said, we've rated it, we've tested it, don't sit next to the engine. Just a thought. So door interlock keeps us out, enclosure keeps the stuff in, usually. So overload shutdown. What's that primarily doing? So this is about stopping imminent bad stuff or shutting down the machine after the bad stuff happened. This is about keeping the bad stuff, keeping us from doing something stupid and getting involved in the bad stuff. This is about keeping the bad stuff from getting to us. Overload shutdown, what's that about? What's it for? Yeah. It's really to protect the machine. So it keeps the machine from hurting itself. Operating a machine after it has been damaged is, of course, the same thing we're trying to fix here, right? Dumb operators. But so if the machine becomes damaged, it won't operate correctly. Things can happen. So this overload stuff is really to keep the machine from damaging itself. It could also keep the machine from catching on fire. Fire could hurt you in a machine shop, especially if it's unexpected fire. What's the purpose of these audio visual indicators? Yeah. So it's really an indicator. It's a way for the operator to know more about what's happening inside the machine, right? So an informed operator is going to be a safer operator. It's a way for the machine to tell us we may be approaching an overload situation. Now, if the overload happens because of too much current draw, so it's an overcurrent sensor. So if we're drawing too much current, what do we also know about the cutting operation? So as we studied our modeling of cutting, what do we know? What do we know is true when the current goes up? Current is power, right? So if the power goes up, what do we know about the cutting operation? Yeah. So yeah, we're using more electricity, but that doesn't really affect the cutting operation that much. So what's the relationship between power and force? Yeah. So the force goes up, right? Because the power equals the force times velocity. And so if the power is going up, that means the force is going up. What does that tell us about the safety of the operation? When the force goes up, what happens? Say again? So the tool might come apart. Tool shatters, parts go everywhere. Pieces go everywhere. What else What else could too much force do for us in a cutting operation? Yeah. Go ahead. Yeah.
Could it potentially break the workpiece?
It could break the workpiece. More likely, it's going to pull the workpiece out of the fixture. The workpiece comes up out of the fixture, flies across the machine, out the open door if we don't have an interlock, through the glass if it's a glass door. Until COVID happened, we would make the Y blocks for your engines. You guys remember that, the very first lab? We made those Y blocks, and you get the big giant tool spiraling down around the part, removing sometimes like 1.5 inches of material in one pass, 1.5 inches wide, not deep. So until COVID started, we actually used to do that lab as a linear thing where each person followed the next one. And we did it on a machine. So those mini mills at that speed have maybe 4 horsepower. We did it on a machine at the speed we were running, we had 30 horsepower. So when you have more power available, what can you do? Crank it up, right? Yeah, so it took like 10 minutes for you guys to make that cut. We were doing it in 2 minutes in the other machine. 5 times faster. What's the risk? I can tell you the risk costs about $1,000 each instance. Yeah.
No, I was gonna say the risk is if there is a catastrophic failure and time to work.
Yeah, the real risk is that you guys have never put a part in a machine tool before, right? What happens if you don't tighten the vise enough? As soon as that tool touches it, it picks that workpiece up, throws it across the machine. Sometimes it throws it backwards. Sometimes it throws it at the glass that's between you and the fixture. Luckily, it's special glass, and it just breaks puts a crack across the piece of glass, and then we have to buy a new one. We have to get approval. We have to put it in. So after the second piece of broken glass, we put a torque wrench on the vise handle for you guys to use the torque wrench. All right, so clearly this wasn't a exhaustive study on the design of safety systems. These are the kind of things that you see in a safety system. When you get out there and become engineers, when you're practicing as engineers, you want to think about the things that these do. So we want to protect the machine from damaging itself. We want to protect operators from doing something stupid. We want to protect operators from the result of something bad happening. So we're going to interrupt the propagation of a hazard. We're going to keep ourselves separated from the hazard. We're going to have warnings to tell us when the hazard might be happening. And training is part of a safety system. And so it's an integral part of the safety system. We do this lecture last instead of first, because at the end of the term, you've got some appreciation of the energy involved in the operations, the forces involved, the loud bangs that happen when something goes wrong. Has anybody heard a loud bang in lab? Most of the hands are up. Yeah. We let you guys screw up. That's mostly what it is, because it's part of the training to help you guys get better. The exam is up. The practice quiz is up. Practice quiz has unlimited attempts. It is the same questions as the exam, with a caveat. There's like, can't remember the exact number of questions, but in each state, but there's some questions that are like multiple choice true false questions. Those are the exact same question. There are 5 questions that are about math. For those 5 questions about math, it is the same problem, but not necessarily the same numbers. And not everybody gets the same version of the problem. For each of those math questions, there's like 10 versions. So you might get the same version of the problem both times. But write down the steps to find the solution when you're doing it in the practice exam. I'll be here again tomorrow to answer questions. We can go through if you're having trouble setting up the question for the math one. I think all the true false multiple guess ones. Well, on the true false ones, you'll get it right in 2 attempts, right? Even if you don't know what the answer is, in the true false ones, you get it right in 2 attempts. With the multiple guess ones, it might take you 5 attempts to get it right. But it allows unlimited, don't game the thing. If you do happen to get the question wrong, figure out why before you do it again. It makes it fast because you could do it in 2 attempts then, because it's not that hard. I think all the multiple guess ones actually have an explanation of what the wrong answer is and the correct answer is when you get it wrong. Certainly have a link to point you towards the correct answer. And then the math ones, if you're having trouble with those, don't freak out. I'll be here tomorrow. So everybody, don't wait until after tomorrow lecture before you start. Take a look at it tonight so that you can come in tomorrow and have intelligent questions. But most of you will be done before tomorrow this time. I have faith, confidence. And I hope to have all of the other grades posted by tomorrow at this time also, so you'll know where you stand. Thank you.